So last time we were talking about the notion of a Serogate loss. So the point is that for computational efficiency, we wish to work with a convex loss function. That was the conclusion of the discussion about convexity. So now we introduce the notion of a Serogate loss. So a function L, and now the function L is taking some vector WB, and it takes some input point xy, is a Serogate loss if the following two things hold. One, we want that for all WB and XY, so last time I called it Z, but it doesn't matter, the loss L of this vector, what? Oh, WB, I can also not have the B here. But we are talking about half spaces. Okay, let me skip the B. It'll be more it will simplify the notation. So we have a half space which is parameterized by a vector W. And I want to know what is the loss of this half space on a point X with label Y. So last time we called this Z. Right? So what do we want to require? We require that for every hypothesis, W, and for every point X, Y, the loss of W on the point XY is an upper bound on the 0,1 loss of W on XY. The 0,1 loss is what we want to minimize. We want to make as few errors as possible. And we want a function that if we get a low error with respect to this function, then we guaranteed that we also have a low error with respect to what we care about, which is just counting the number of misclassifications. And the second requirement is that for all xy, this function L as a function of, if I fix the parameters xy, is a convex function of W. So last time I put here a dot, and it was confusing to some people. So it's a function. You see, originally, this function has two parameters, two inputs, W and the sample point. If I fix the sample point, it becomes just a function of W. So if it is just a function of W, it's a function over vectors, and I can talk about the convexity of such a function. So we want that this function will be convex. So that's our requirement for a Serogate loss. Is any question? And the only Serogate loss that we will talk about, I mean, in the literature, people do use in practice several types of Serogate loss, but the most common one and the only one that we'll discuss is called the Hinge loss. So the definition is that the hinge loss hinge of a point, of a vector W or a classifier W on a point xy is defined as the maximum between 0 and 1 minus y times the vector xw. So let's see what does it mean. And so note that this w times xw is our predictor is trying, we try to predict with h of x equals the sine of xw, right? That's the hw of x. That's the predictor that is parameterized by the vector w. Yes?
These brackets around xy are round brackets?
There should be round brackets. You're right. It's not an inner product. Thank you. So these should be round brackets. Thank you. Okay, so this is, but these brackets mean the inner product. Okay, so just remember, we are trying to predict with the sign of this dot product. So when we are correct, W is the sign that we are given on the point. So when we are correct, the sign of xw and the sign of y are the same. So when we are correct, this is positive if and only if hw of x equals y. So when this is positive, our loss is going to be less than 1. If this is negative, our loss is going to be more than 1, because we are taking here 1 minus something which is negative. And furthermore, when will the loss be 0? When will this hinge loss be 0? The hinge loss becomes 0 once we are correct and this dot product is at least 1. See, if this dot product is at least 1 and we are correct. Correct means this becomes a positive number. And if I deduce from 1 something which is at least 1, y is either y is in plus 1 minus 1. So if I deduce something which is, subtract something which is more than 1, then this becomes negative and the maximum becomes just 0. So the loss becomes 0 once the label is correct and this dot product is more than 1. Now, so we can draw it. So if I want to draw it on a graph, so here this is going to be the loss. Say this is 1, and here is 0. And this is going to be y times w dot product with x. So how will our loss behave? If y times the dot product is positive, that is, we are on the right side of the hyperplane, and bigger than 1, then my loss will be 0. So the loss will be 0 here. Once the inner product becomes less than 1, then I have here a linear function. It's 1 minus this loss. So I get here a straight line that goes like this. This is 1. And once I'm making a mistake, this becomes a plus. So my loss is more than 1 because I get here a plus. This is negative if I made a mistake. with this minus, it becomes a plus. So my loss is more than 1 when I'm making a mistake. And when I'm not making a mistake, my loss becomes 0 if this product is big enough. So let us see, first of all, that this loss satisfies these two requirements. And then we'll discuss more why it makes sense to have this loss. And we will show bounds in terms of this loss. Bounds on our error in terms of this loss. So first of all, I want to show you why is this function. I want to show that this loss, the hinge loss, satisfies these two requirements. So the first thing I have to show you is this is convex. So my first claim 1, is that L hinge is L hinge of some input and a point xy is convex for all xy. And why is that? And this goes back to our discussion of convexity. Because this is a maximum of two functions. You remember that we saw that if two functions, if each of them is convex, then the maximum is going to be convex. So as a maximum of two convex functions, it's a convex function. And this function is convex. We had a concrete statement about that such functions are convex. So this is a convex function. Just it goes back to our discussion of what are convex functions and the closure of the family of convex functions. And the other claim is also quite simple, that the hinge loss L hinge of W and the point xy is always greater or equal than the 0, 1 loss for HW on a point xy. Because what is the 0, 1 loss? The 0, 1 loss of my classifier HW is 0 when I don't make a mistake. But when I don't make a mistake, the sign of this is the same as the sign of y. So it is 0. The usual loss is 0 all the way up to here. And once I make a mistake, it becomes 1. So the 0, 1 loss behaves like 0 whenever this is positive. So whenever this product is positive, my 0, 1 loss is 0. The minute this product is negative, which means the sign of y is not the same as the sign of the inner product, it becomes a 1. So that's the 0, 1 loss. And it's always below the hinge loss. And just note that all this discussion, I can add here a b, and it'll be the same thing. So I can talk about the loss of not just homogeneous half spaces, but half spaces that look like h of x, h, w, b of x, which is the sign of a w dot product with x plus b. And I can talk about the hinge loss of this. It's just that anywhere I have here w, I'll replace it with wx plus b. Because my prediction is with the vector wx plus b. But without loss of generality, we can settle for homogeneous half spaces without a b. OK, so that's the hinge loss. So that's a loss that we are going to use to get convexity, to get efficiency of the computation. So let me describe now a little bit what is the geometrical meaning of this. So what I claim is that what this loss is going to do, it has to do with the notion of margins. So it's an important notion, the margin of a linear classifier on a sample. So if I have a sample assume that I have a sample of points. And I'm trying to do, so say all of those are pluses and all of those are minuses. And I'm trying, this is my sample S, and I'm trying to find a half space to predict with. So this is my sample S. So usually we would like to find H. So this is S. This is my sample S. So usually we would like to find an H that belongs to argmin of the loss of H, the 0, 1 loss with respect to S. But so what is this argmin in the picture that I give you here? What is the minimal loss of any classifier on this set of points? Yes, 0. Because we have classifiers that just don't make any mistake. So this is going to be 0. But the point is that there are many classifiers with 0 error. So I could pick this guy as a minimizer of the loss. And I could also pick this guy as a minimizer of the loss. Or I could also pick this guy, H3, as a minimizer of the loss. All of them have 0 error. And the question is, which of them makes more sense that I'll pick it? If you had to choose the classifier, so we have some unknown distribution. We saw a sample. The sample had positive points and negative points. We see that I can separate them with a linear half space. Which one makes more sense to choose? Just on a very intuitive level. Yes? H2 makes most sense. Why H2 makes most sense?
It's like same distance from upper and lower plane.
Yeah, it's kind of balances the distance. The other consideration is that, I mean, those points were just drawn from a distribution. If I pick a hyperplane like this, then if the distribution has even one point that is a little bit, it is plus, but it's a little bit different than this point, then I'm already going to make a mistake on this point. But with this guy, I'm robust to perturbations. If the distribution has points which are sitting close to those pluses and minuses with the same sign, I'm not going to make a mistake on them. So it makes sense to pick a classifier with a large margin. Now what I claim is that this consideration of large margin is consistent with trying to minimize the hinge loss. And why is that? Because there is a close connection between this product and the margin. So let me show you the connection between this product and the margin. Then we will see why picking a classifier with a small hinge loss corresponds to picking a classifier that has a high margin away from the points of the sample. So my next claim is, so we want to define the margin of a point from a hyperplane. So given a linear classifier or a linear function which is determined by WB. So the linear function is just the function f of x or h of x. F of x equals w dot product x plus b. And a point x. Let us define the margin of w of f with respect to x by, so here is my line, this is f, and here is a point x. How do I want to define the margin? I want to define the margin as the minimum distance between my point and the line. So I want to talk about the minimum distance between my point and the line. How do I write it in a formula, this minimum distance? So it's a minimum distance between, this is my point x. It's a minimum distance between my point and any point that lies on the line. So it's the minimum of the distance x minus u such that, how do I say that u is a vector that lies on the line? Yes?
Dot product of u and the line is 1. You're saying on the line? Or
on the line. I want the minimum distance between x and the point u on the line. So I can pick many u's here, but among all the u's that lie on the line, I want to pick the one that minimizes the distance to x.
Then u minus x, the vector u minus x dot the vector of the line is 0. You want them to, right?
I just want to say u is on the line. So, I mean, if you have this equation, so look, if I want to tell you have a line which is determined by x, ax plus b, this is f of x. How will you tell me that the point is on the line? Oh, say f of, yeah, yes?
So just to clarify a point, the point x and the x in our function are different x's.
Are different x's. The x in our function is a general x. That's a variable. And here I picked a concrete point.
Right.
So maybe I should call it x0. I picked a point x0, and I want to define its distance to the line. So I'm saying the distance to the line is the minimum distance among all the distances to points on the line. How do I say that u is on the line? U is on the line if when I substitute it in the equation of the line, what do I get? If a point is above the line and I substitute it, I get a positive number. If it's below the line and I substitute it, I get a negative number. So if it's on the line, what do I get when I substitute it? 0. Such that w dot product u plus b equals 0. This is just saying u is on the separator. So this is my definition of the margin. It's the distance between the point and the closest point on the line. And now I make a claim that connects it to what we are measuring here in the hinge loss. So the claim is that for every x in some, it doesn't matter, some RD, and W in RD and B in R, if the norm of W is 1, then the margin of a WB with respect to x equals exactly Wx plus b, its absolute value. So it turns out that if I substitute x here, what I get is just this margin. And that's exactly what I'm measuring when I'm doing the hinge loss. Yes?
I don't get why W dot product U plus B will equal to 0.
What? Okay, so let us look at, yeah, it's a good, it's a point that I want you to understand. So let us look, what is the, assume, let's go into two coordinates. So I assume that I have a line, and this line is determined, I mean, I look at the function, which is 3x plus 2y minus 7, oh, here it is, plus 7. This is this line. So to determine what is the, if I have an equation for a line, so here my w is the coordinates of the coefficient 3 and 2, and my b is 7. And which points lie on the line? So the line is just a set of all points. The line is just a set of all points. Or well, let's call it not y, but let's call it x1, x2. So we will not be confused with the y, which is the label. So the line is the set of all points x1, x2, such that what? Such that 3x1 plus 2x2 plus 7 equals 0. These are the points on this line. Yes?
Round brackets.
What?
Round brackets.
Round brackets again. You're collecting a lot of points today. Right. The graph of a function is the set of all points on which we get the points. Like the graph of a line is just a set of all pairs xy, x1, x2, such that I get 0 here. Yes?
But the way you define f of x is exactly the same equation.
Is exactly the same equation.
So which means if for all u that is on the line, that equation evaluates to 0, it means that y is always 0, isn't it?
If u is on the line. So when I use this as a classifier, what is HWB of a point x? How do I classify with this? I look at the sign of wx plus b. This is how I use it as a classifier. So the sign for all the points which sit here will be 0. But for points that will sit here, it will give them label minus. And for points that will sit here, it will give them the label plus. If you take a point, you look at this line, right? And take the point x1 equals 10, x2 equals 10. Where will this point lie? x1 equal 10, x2 equal 10. It will be above the line. And that is the same thing as saying that when I substitute 10 here, I get a positive number.
What I mean is that, let's say, what would be the value of f at u?
What?
What would be the value of f at u?
F of u is I just substitute. This is the value of f of u. F of u is just take this dot product and add b.
That would be on the line, right?
No, that will be, if u is on the line, the value will be 0.
Oh, okay.
So what I'm saying is, where is u? And what, here I say, what is the value of w dot product u plus b? So if u is under the line, this is going to be negative. On the line, it's going to be 0. Above the line, it's going to be a plus number.
So the line is defined by w, not f of x.
The line is defined by w and b, and that's my function f. B also plays a role.
No.
Okay, yes.
Is think it might be a bit confusing that it looks like you labeled the line as f, when really the line is f equals 0.
The line is the graph of f. Right, it's the point. Right, you're right. The line is the set of all points where the value is 0. This is the line. This is the graph of the line. The set of all x, y such that this is 0. Okay? So what I'm just trying to tell you is that we're using this for classification all the time, linear classifiers. And I'm just trying to give you what is the geometric interpretation of this. And the geometric interpretation is that if I take a point and I evaluate this, not just the sign. The sign tells me whether I'm above or below the line. If I evaluate the actual value, what I'll get is just the distance to the line. So let us just, this is now very simple algebra, and just to check that this is indeed the case. So let me do this algebra quickly. So there are two claims here. If I want to tell you that the margin equals exactly this, I have to show you. Remember, the margin was the minimum over all v over all u of the line of x. So here is the point x. Here is the line which is determined by w and b. How will I pick this point here that minimizes the distance to the line? Algebraically, how will you pick this point? If you have say, a linear space and a vector outside the linear space, anybody remembers how do I find the distance between the vector and the subspace? What I do is to find the minimum point. X is a vector. This is the vector w. I project x on w. So the projection gives me this guy. And then I take the difference between x and the projection. The difference between x and its projection on the line gives me the distance. So what is the projection? Algebraically, what is the projection of x on the line? So the projection of x of the line is this vector. This vector is going to be the vector w dot product x plus b. This is just a number. And I take this number along the direction w. That's the projection. So this guy here, the distance, so let's call this vector v. V is going to be the vector which is x minus wx plus b times w. This vector v is the difference between x and the projection of x on w. The projection of x on w is I take the dot product and I take it along the direction of w. So I claim two claims. One of them is that if I take really the distance, this v is really what I wanted, is really this number. And secondly, that this is really the minimum distance from all the points on the line. So I need to make two claims. So just recall, what we are looking for, we are searching for, is the minimum over all vectors u on the line of the norm of x minus u, the minimum of the norm of x minus u over all u on the line. So I'm claiming that this is it. So the first thing is that Okay? So I want to show you, first of all, that this point U is on the line. I mean, I feel like I'm burning too much time on the algebra, and it's not as important when we are 3 weeks away from the end of the course. So, so what I'm claiming is 3 things. That this point U is on the line, that the distance between x minus this v, x minus v, is exactly what I wanted. What is x minus v? It is the square root of the dot product x minus v, x minus v. And x minus v, it's the same. I just do x minus this, so I just get this part. So it's the dot product. Oh, here I do need. Right. Here I do need these brackets. What is x minus v? X minus v is a w x plus b. This is a constant times w. And the same thing, x minus v again. W x plus b times w. So what this equal is, this is a number. So I get this number square. And w dot product w is the length of w square. So I get here w x plus b square times the norm of w square. And now I take the square root, so I get exactly what I wanted. Wx plus b. Okay, so lots of hands, so I must have forgotten or something. Yeah.
I'm missing some angle brackets on this sector and the square root and the whole.
I'm missing square brackets here. Angle brackets, right. I'm missing angle brackets here. Yes?
Also, it doesn't really matter since we multiply it together, but really those wx plus b terms should be negative, because x minus v, we lose the x, and it's like these negative terms.
It's 2 minuses, right? If I do x minus v, I do x minus this thing.
Yeah.
So the v, the x goes away, and here I have minus minus. Okay? I mean, it wouldn't have made a difference because you square it, but it is okay. Yes?
Sorry, is v a point on the line, or is v the distance between?
No, v is the distance between x and its projection on the line. I claim, now I need to show you that this is a point on the line. Right. That that's a point on the line, and that this is better than any other point. So I will not do these 2 claims just because I'm really burning too much time on this. So the 2 missing claims are that note that u equals the dot product wx plus b times w is on the line, just because it's a vector w multiplied by some constant. And the next thing is, and this is more difficult, another claim is that for every u prime on the line, we get that x minus u prime is greater or equal than this x minus the u that we picked. So this is really the minimum. Yeah?
I'm still a bit confused. So what's the claim that you're proving with that first equation?
The claim that I want to use is the minimum distance between x and the point on the line is this substitute x in the equation of the line. So what I want to claim is that if I want to know, I mean, we had two notions. We have this notion of a margin. And the margin was the distance of a point from the line. So I'm saying we can easily calculate this margin by just substituting the point in the equation of the line and taking the absolute value.
But
So
isn't V the margin as opposed to x minus? So it's just,
what?
I thought, isn't V the margin instead of x minus? Or isn't it?
Oh. Okay, yeah, that's a good yeah. Yeah, what I did here, right. I didn't,
Should those all be U's?
oh, now I got confused between U's and V's, right? Okay, okay. V, no, okay, so everything's okay. V is this vector. I want to show the margin is the norm of this vector. So I want to calculate the norm of this vector.
So shouldn't you be looking at the norm of V instead of the norm of x minus?
X minus u, like the norm of x minus u, the norm of v. And so you meant to put x minus u.
This x is a vector.
Right. Right. So,
So the x's are not the same.
You should put a bar on it.
that's really terrible. Once I'm realizing I'm behind in time, then things get slower. I have x here. I want to look at x minus. So this is my v. Right.
Just move on to the next thing.
Right. So what I needed here is just the. Okay. So I call this u. Right. So what I want is the norm of v. And that's x minus u, x minus u, and this is u. And everything is right. This is just the vector v itself. It's not x minus v. Okay, sorry about that. Yes?
Do we have to know those algebra for the exam?
If I get confused on the board, then you don't need to do better than me on the exam.
Good enough for me.
Okay, so what I'm claiming, the only thing that I wanted to prove here is that by substituting a point on the line, we get this number. It's the margin of the point from the line. And now we can go back to the hinge loss. So the hinge loss was, remember, what was the hinge loss? The hinge loss, L hinge of W and a point X with label Y was the maximum of 0 and 1 minus the dot product Y times the dot product XW. Now, if we go back here, notice what will be the hinge loss if a point here, if I have here a point, some point X, and its label is plus. What is going to be my loss? So Y equals plus 1. What is going to be my loss on this point? So my loss on this point is going to be the maximum between 0 and 1 minus. I mean, since my line labels this as plus and this as minus, this dot product is plus above the line and minus below the line. This thing is going to be always positive when I predicted the label correctly. So if the label is correct, for every point which is a distance at more than 1, my loss, what's going to be my loss on every point which is of distance more than 1 in the line? Yes? 0. Right. For every point which is more than distance 1, I'm paying 0. For every point which is inside this margin, how much do I pay? I pay the distance of this point from the boundary. Because we said the distance of this point from the boundary, I mean, you can ignore the b, because for simplicity, we assume that b was 0. So I'm paying 1 minus the distance to the boundary. So if I have a point here, I'm going to pay this. This is my loss. The closer I get to the line, the more I pay. When I get to distance 1, I stop paying. All those points are classified correctly, and I don't pay anything. As I'm getting close to the line, I'm paying for being close to the boundary. And once I go to the other side, I'm just paying the distance. I'm paying 1 plus the distance to the line. Once I misclassify, this becomes a negative number, so my loss is 1 plus this distance. Yes?
Is there any reason why we pick 1? I mean, if your data set is really, really sparse, maybe this doesn't give you anything over the 0, 1 loss. So
Right.
Intelligently pick what constant to put.
Right, so that's a very good point. In the definition of the hinge loss, we picked here 1. We could have picked any other constant. This is a choice that we make, and it will not change the discussion. So I picked 1 just for simplicity.
But in actual application of this,
In actual application, it's a matter, we will see in a second, it's a matter of I can scale up all the points to make this 1 meaningful. Okay, so what is the bottom line of this discussion? The bottom line of this discussion is that the hinge loss penalizes you for correctly labeled points if they are too close to the line. Once they are away from the line enough, once I have enough margin, I'm not getting penalized. For misclassified points, I'm penalized all the time, and the penalization grows as I'm getting further away from the line. But for correctly classified points, so if I have my line here, I'm paying here for correctly classified points, but every correctly classified point outside does not cost me anything. Yes?
So we're not actually maximizing the margin, we're trying to get it to at least 1.
We're trying to make the margin into at least 1. Right. We're not maximizing the margin, but we're trying to make the margin at least 1. Right. Okay, so this is the geometric intuition behind the hinge loss. Yes?
All of this is under the constraint that W has a norm 1, right?
Yeah, under the constraint that W has a norm 1, and I'll get back to it in a second.
That's not convex.
What?
The space upon W is norm 1.
No, but that's, yeah, but we will do it under the restriction. It's a good point. We want to restrict the W's to a convex set. We will restrict the W's to all W's of norm at most 1. But if I have a W of a smaller norm, then by increasing W, I'll increase the margin. It will work well for me. So I will always choose something which is exactly 1. But I'll discuss it in a second. So what is So now what the algorithm is going to do is the algorithm is trying to minimize the hinge loss instead of trying to minimize the 0-1 loss. So our learning algorithms will aim to minimize the hinge loss rather than the 0-1 loss. Now, if we get a guarantee, we can, you remember that our discussion of losses and learning and so on and ERM was independent of the type of the loss. So if we get, so assume we end up we output a classifier H, then what we will get is that the loss with respect to 0-1, the 0-1 loss with respect to the distribution or to P of H is bounded by the hinge loss with respect to P of H, which, if we had successful learning, we know that this is going to be at most the minimum over all H's of the hinge loss of LP hinge of H plus some epsilon, right? If we had epsilon successful learning, then in the agnostic setting, what we claim is that we manage to find some H that competes with the best in the class, minimum of all H's in my class, of the hinge loss of that H plus epsilon. That's what we are trying to do. We have some loss. We're trying to compete with the best in the class. But now we want to know what does it mean in terms of the 0-1 loss. So I can rewrite it, just change it a little bit, and rewrite it as, so this in itself is equal to the minimum over all H's in my class, which are all half spaces, of LP hinge of H minus L01 minus the minimum over all H in H of L01 of H plus the minimum over all H in H of L01 of H plus epsilon. So I didn't do anything, right? I didn't change anything. I just did minus and plus this. But this allows me to kind of understand what is my error composed of. Again, a learning algorithm is trying to minimize the loss. The learning algorithm is epsilon successful if what I output gave me a loss which is not away more than epsilon away from the minimum possible loss. So this was just the assumption that I got an epsilon successful learning algorithm. But it minimized the hinge loss, and what I care about is the 0-1 loss. So I want to compare it to the 0-1 loss, so I add and subtract the minimum that I could get for the 0-1 loss. And now I can divide it into three types, three components of this arrow. This arrow is due to the fact that I was using hinge loss, minimizing hinge loss, instead of minimizing 0-1 loss. So this term is due to minimizing due to the algorithmic complexity consideration. Due to the algorithmic complexity, I was minimizing the hinge loss instead of minimizing the 0-1 loss. And how do I know that this is always positive? Right? Why? Hinge loss is always bigger than the 0-1 loss. Now, this thing is what we already call the approximation error. Right? This is inevitable. If I'm trying to predict with a member of the class H, I cannot do better than the best one in H. So this is due to the choice of my class. I want to choose a class that has a small approximation error. And this guy, this epsilon, is the generalization error. And this is what we bound with all our analysis. This will goes to 0 when the sample size goes to infinity. This is what our theorems are proving. What our theorems are proving is that our sample size goes to infinity, this guy can go to 0. So we have 3 components of our loss if our algorithm is minimizing the hinge loss. I can draw it in a picture, so you can think of it this way. So assume that this is the space. This is my possible classifiers, and this is the base F base. So this is the best predictor for my distribution. This is what I would like to use, the best predictor of the distribution, the best possible. Right? Now, since I'm restricting myself to classifiers in H, the best that I could do is this guy. What is this guy? This one is the minimizer. It's the minimizer of L01 of H over H in H. It's the best H with respect to the 0-1 loss. But instead of trying to find this H, due to the considerations of convexity, I'm not shooting for this H. I'm shooting for another one. This is minimizer of hinge loss. That's the one that I'm shooting for, because I don't know how to find. And I also make here another arrow, which is due to this is the epsilon, and this is due to the fact that I'm only using a sample rather than using the full distribution. So this arrow, this is what actually A of S gives me. So A of S gives me what is best with respect to the sample. What is best with respect to the sample is epsilon away from what could have been best. But what I'm shooting for as could have been best is the minimizer of the hinge loss. So I have here 3 types of arrows. That's the approximation error. This is the generalization error. And this is the error due to the fact that I was minimizing hinge rather than minimizing the 0-1 loss. So I'm saying my total error decomposes into these 3 components. That's what this equation tells us. Yes?
Sorry, I'm a little bit confused. Is the H that is generated a member of the big class H?
Yeah, my big class H will be the class of all linear classifiers. So I'm outputting a linear classifier. I will output a linear, because our optimization problem is find the linear classifier of norm at worst 1 that minimizes the hinge loss. That will be a convex optimization problem.
So why did we draw the final error outside of the H bubble?
Because the H bubble is, I mean, you have some phenomena. I want to predict whether a patient will recover or will die. So I have here all kind of measurements of the patients. Nobody promises me that this is going to be linearly linearly separable. Maybe the pictures look like this. I have a minus here and I have a plus here. But so my best classifier is this guy. But it still makes an error. This is this error. Because I'm predicting with a half space, and maybe the phenomena is not separable by a half space. So this is due to the choice of my class. And this is due to minimizing hinge instead of minimizing 0-1 loss. And this is due to working with a finite sample instead of having infinite many examples and being able to estimate the distribution. Yes?
So one of the losses comes from all of the H outside of H. In this case, are F bays. So in this equation here, we have all of our error terms in terms of H element of H. Is really the approximation error sort of H?
Right. So again,
Sorry, just F base is not in our classifier hypotheses.
Right.
It's contributing the approximation error.
The approximation error is due to my gap from the F base. From the base, right.
It's the loss. It's just for minimum.
Okay.
It's the best it's the function that will give you minus here and pluses here.
There's like an implied minus 0 here, right? That's basically the point. The F base is the 0.
The F base is the 0 here, right. This is, I assume that the F base is the 0.
Right. That makes
Yeah.
sense.
That's my 0. That's the best you could hope for. And on top of it, I'm paying due to choice of the class, due to convexity, and due to using a sample instead of full distribution. Yes?
Can't base have a loss bigger than 0?
Okay, so let me ask you this question. Can the base classifier have loss bigger than 0? When will the base classifier have loss bigger than 0? Yes? When the labeling is not deterministic. When the labeling is not deterministic, you remember F base, when you give it a point x, it tells you, let's predict plus if the p of the label of x, y given x is greater or equal than half. And let's predict minus if this is less than half.
But then, so then the approximation error isn't just the gap between F base and...
No, this is there is also the error of F base. And the error of F base is due to non-determinism. It's due to the fact that things may be random. So I kind of here took it to be 0. Assume that the labeling is fully determined by the features. So F base can make an error when our labeling is not deterministic. But that's kind of the most one of the important lessons of this course, is that when we are doing learning, we are suffering all these types of errors together. And we're trying to minimize this sum. We pick a class. We want to pick a class with respect to which I can approximate well the phenomena that I'm trying to approximate. I want to pick a class of small VC dimension because then this epsilon will be small. And I have to worry about computational efficiency. And that gives me another cost. So these are the three considerations that are playing the game. This is due to my prior knowledge. How did I pick the class? This is a cost to picking a too big class. The more prior knowledge I have, I can save on this. The more uncertainty I have, I need a big class to make sure that I'm getting close to the optimum. And then there is the computational cost. So we really ran out of time, but let me just, to conclude this discussion of what we are actually doing in the hinge loss, let me just give you results that I will not prove. So the most common learning paradigm for linear classifiers is the SVM. SVM, I'll support vector machines. I will explain more what it means next time. What is the SVM paradigm? The SVM paradigm is the algorithm that works like this. So A of S, you get a labeled sample S, and A of S is trying to find a half space. So the half space that I'm trying to find looks like argmin. I'm trying to minimize the following. I'm trying to minimize some parameter lambda times the norm of W plus L hinge of W on S. This is what my paradigm is trying to minimize. So trying to minimize the norm of W is very similar to trying to maximize the margin. So this is kind of trying to maximize margin while not paying too much in terms of the hinge loss. So this is the most, and the point to note is this is convex, and it gives us a generalization result that I guess, okay, I'll tell you what is the generalization guarantee that we get for this algorithm. The guarantee that we get for this algorithm is that the expected loss over all samples, the expected loss with respect to the distribution, 0, 1, this is what I really care about, of my classifier is going to be bounded by the minimum over all W's of norm at most 1 of the hinge loss, L hinge of W with respect to a distribution, plus a term that looks like exactly the term is 8 rho over m, but okay. So what is happening here? What I'm saying is that we are using an algorithm that tries to minimize the norm plus the hinge loss. The advantage is this is a convex function. So we know how to carry it out efficiently. If we do this, we get a guarantee that our error is bounded by the best possible hinge loss over all vectors of norm at most W, plus a term here that goes down with m, and the rho is the maximum over all my x's over all x of the norm of x. So it really depends on where do my points lie, because the hinge loss depends on how far are the points from the origin. So basically what I'm saying is that by minimizing the hinge loss, we get a convex task. We can carry it out. By doing this convex task, we get some kind of a bound that contains those three types of error that we saw here. So next time I'll explain it more and explain more about the support vector machines paradigm and how do we actually work with it.